Chapter 11 was the last chapter we looked at in Unit 3, Weather. We started off Chapter 11 by looking at a demo of dry ice undergoing a process called sublimation. Sublimation is a process where a substance goes directly from the solid phase into the gaseous phase, and that's what both of these diagrams are representing. We use it to show how dramatic the difference is in volume when a solid turns into a gas, and how much space a gas actually occupies, about 800 times more space than that of a solid. So we covered that phase change. We also looked at the phase change of vaporization and evaporation. Solid to gas is sublimation. Liquid to gas is boiling or vaporization. The process of vaporization and evaporation, they're related but different, and that boiling occurs at one single temperature. So for water example, you have to bring the temperature up to 100 degrees Celsius if you want all of the water to boil. It happens throughout the entire sample of liquid, where evaporation can occur at any temperature because it's only the surface molecules of the liquid that are turning into a gas. Because remember, we looked at that in a sample of matter, all the particles don't have the same amount of energy. So in any given sample, some of them do have enough energy, high energy, to turn into a gas, and they do. We looked at the distribution of air molecules, gaseous molecules in the atmosphere, to make the point of there are more of them towards the surface and less of them as you increase in altitude or increase in elevation. And we use this to introduce the idea of pressure. And we did a bunch of pressure demos, and we came up with a really simple definition for pressure. And we looked at it as the force applied over a given area, but what we focused on in chem was gas pressure, right? And it comes from the collisions that gas molecules make with the container walls. And I did a bunch of different demos to try and emphasize pressure acting in several different ways. Relating it back to the atmosphere, if we're looking at pressure as the number of collisions, because there's more particles near the surface and less as you increase in altitude, the pressure is higher down here, the air pressure, because there are more molecules, therefore there's more collisions that are being made, and the pressure decreases as you increase in elevation because there are less molecules and therefore less collisions being made. So the one thing we tied pressure back to in explaining why pressure would increase or decrease is coming from the number of collisions. Here are examples of gas particles that are in a container. Every time they collide, they are introducing a pressure, quote unquote, to the system, and that's what we are registering. Like if you put a pressure gauge inside of a tire, it's registering how often the gas molecules are colliding with it. One of the demos that we looked at was an air pressure mat that I put on the table and was able to lift the table up, but a suction cup works the same way. When you push a suction cup down onto a surface, you're actually just eliminating all the gas particles in the suction cup, or in between the suction cup and the surface here. So there are less gas molecules on the inside than the outside, so the pressure, then the collisions that they're making on the outside are greater, and therefore the pressure is actually just forcing this suction cup to stay on whatever surface it is. It's really being pushed down on the table. We said suction really wasn't a thing. The idea of pressure introduced us to our last two gas laws. The first one here is Boyle's law. Boyle's law was P1 times V1 is equal to P2 times V2. It was looking at the inverse or indirect relationship that gas pressure has with volume, and we get this curve. We called it a hyperbola. It was asymptotic to the x and the y-axis. It was not linear. It was not a direct relationship through 0, 0. What this is saying, the fact that it's indirect or inversely related, is that as one variable goes up, the other goes down, and vice versa. How do we explain that? Well, if we have a sample of gas here and we decrease the volume, now the particles, we haven't changed the temperature. right? That's constant here. So the average kinetic energy of the particles is the same. So they're not moving faster. That's one important piece to understand here. If we're not changing temperature, the average speed's not moving. What is changing is how far the particles have to move before they make their next collision. There's just a less occupied space here. So because there's less space to move, they're going to make more frequent collisions in the container. And again, going back to pressure, more collisions means a higher pressure. Let's look at a couple of examples here. A sample of oxygen gas has a volume of 150 milliliters when its pressure is 0.947 atm atmospheres. What will the volume of gas be at a pressure of 0.987 if the temperature does not change? So again, we have Boyle's law. You could start with the combined gas law here. P1 is 0.947 atm. V1 is 150 milliliters. There's no restriction on the units here because there's no temperature. The units just have to be the same on either side, the pressure unit and volume unit. We want to figure out what the new volume is when the pressure changes to 0.987 atm. What we should do first is make a prediction. Our prediction is going to be, because the pressure is increasing and the relationship between pressure and volume are inversely proportional, the volume is going to decrease. That would be the only explanation for why the pressure is increasing, why the gas molecules will be making more collisions. I'm going to divide both sides by 0.987. So 0.947 times 150 divided by 0.987. We're going to get a final volume of 143.9 milliliters. Second example, if I have 5.6 liters of a gas in a piston at a pressure of 1.5 atm and compress the gas until its volume is 4.8, what will the new pressure be? So 5.6 liters, my initial volume, the initial pressure is 1.5 atm. It's going to be equal to, I'm changing the volume to 4.8 liters here, and I want to find what the new pressure is going to be. Now again, the volume is decreasing, so the only thing that would make sense for pressure to do would be to increase. Decreasing the volume is going to be less space for the particles to move. 5.6 times 1.5 divided by 4.8, I get pressure is equal to 1.75 atm. So yep, pressure goes up. That makes sense. The last gas law, individual gas law that we looked at was Gay-Lussac's law. Gay-Lussac's law was relating pressure and temperature. Again, this looks like Charles' law is a direct relationship. As temperature increases, pressure increases. How do we explain that? Well, if we have a sample of gas here, this has to be now a rigid container, meaning this is locked. The volume is not changing. If the volume was changing, then you get a scenario that's either Boyle's law or Charles' law. Boyle's and Charles' law both occur in flexible containers, so the volume can change. If the volume is being held constant, the container is rigid, something like a glass bottle or a metal canister. You have a sample of gas in here. The number of particles are not going to change. As you increase the temperature, you're making them move faster. They're going to want to expand like Charles' law, but because they can't, they're in a rigid container, what's next that increases is the pressure. Because they can't expand, they just end up moving faster and making more frequent collisions. More frequent collisions means higher pressure. A steel container of nitrous oxide is at 10.4 atm. It's cooled from 33 degrees Celsius to negative 28 degrees Celsius. What is the final volume? What I should be thinking of right now, and what you should be thinking of as you're reading it, is we need to get rid of these Celsius temperatures. Remember, this relationship is the temperature versus pressure, but temperature in Kelvin, because that's what forms a direct relationship. So I must convert those two values to Kelvin before I plug them in. Your initial pressure is 10.4 atm. Your initial temperature is 33 degrees Celsius, which in Kelvin is 306. We want to find out what the final pressure is when we cool it to negative 28. Again, we should make a prediction. This is 245 Kelvin. Make a prediction about what's going to happen. You're cooling it, the particles are moving slower, which means they're going to make less frequent collisions. The pressure is going to decrease. I'm going to cross multiply 10.4 times 245 is equal to P2 times 306. And if you do the algebra correctly, which you should stop and make sure you can do, final pressure is equal to 8.3 atm. The gas in an aerosol can is at a pressure of 3.0 atm at 25 degrees. The can warns not to allow the temperature to get above 52 degrees Celsius. What would the pressure of the can be at 52 degrees Celsius? So P1, 3.00 atm over 25 degrees Celsius. We're going to convert that to Kelvin right away, 298. What's the final pressure? If we increase the temperature to 52 Celsius, which is a Kelvin temperature of 325, take a minute, stop and do the algebra. You should get 325 times 3 divided by 298. And you get 3.27 atm. Again, makes sense because we're increasing the temperature, so we expect the pressure to increase. Last thing we looked at was, now that we had all these different gas laws, was looking at how we can actually combine them, right, into the combined gas law, which is P1 V1 over T1 is equal to P2 V2 over T2, and it's great because we can actually start there and then cross out any variables that are held constant and derive the law that we actually have to use. A sample of helium gas has a volume of 0.180 liters at a pressure of 0.8 atm and a temperature of 29 degrees Celsius. What is the new temperature, so T2, of the gas at a volume of 90 milliliters and 3.2 atm? Everything's changing, and the reason we have this is because realistically, everything is probably going to change in an experiment. It's really hard to keep one of these variables constant. So let's plug in what we know. The initial pressure is 0.8 atm. The initial volume is 0.18 liters. The initial temperature is 29 degrees, but again, it's Celsius. That throws up a red flag. Convert it to Kelvin, you get 302. Is equal to final pressures 3.2 atm. Final volume is 90 milliliters, and we want to solve for final temperature. Now, the next thing you should look at, whether you catch it here or catch it when you plug it in, are the units, right? The only restriction on units is that the temperatures have to be in Kelvin, but the temperatures for, or the units for pressure and volume need to be the same. They have to be consistent. Pressure's in atm, one volume's in liters, one is in milliliters, so you have to change one of them. I'm going to change this to 180 milliliters. If you change 90 milliliters to liters, you're going to get the same answer. So if we do the algebra here, 3.2 times 90 times 302 divided by 0.8 divided by 180, you should get a final temperature of 604 Kelvin. You can leave it like that. If they wanted the temperature in Celsius, you would have to subtract out 273. A sample of nitrogen gas in a constant volume container is at 25 degrees Celsius and has a pressure of 2.5 atm. Determine the temperature if the pressure is increased to 4.25. Now, they say constant volume, so what we can do here is take the volume out of the equation. We're left with Gay-Lussac's law, and then we have 2.5 atm as my initial pressure at 25 degrees Celsius, which in Kelvin is 298. Changing the pressure to 4.25 atm, we want to solve what the final temperature is. I'm going to do 298 times 4.25 divided by 2.5. Gets us 506.6 Kelvin. Makes sense? Yes, the pressure is increasing. It almost increased double. The last thing that we looked at was, especially for the combined gas law, the idea that all these things are going to be changing at once, was in the atmosphere. And we looked at this using a weather balloon, and we looked at the example of the stratosphere jump by Felix Baumgartner, that these weather balloons, when they fill them up, they have to calculate how much gas they put in because the volume is going to change as it increases in elevation. And for two reasons, we have two things that can happen to the volume, right? As you increase in elevation, two things happen. The temperature decreases, so that should cause the volume to decrease. But the pressure also decreases, which should cause the volume to increase based on their respective laws. And we looked at, obviously both of those can't happen, or if they did, they would cancel each other out. But that's not what we see. When the weather balloons released, we saw how full it got when he finally got to the stratosphere. And the same thing happens with weather balloons. So in terms of the atmosphere, the decrease in pressure actually outweighs the decrease in temperature. The pressure change is so much greater than the temperature change, is really what that's saying. Then the very last thing we looked at was cloud formation in terms of temperature and pressure. We looked at air masses last chapter and how they act when they are warm and cool. When air masses cool and drop in temperature, they are more dense, so they will sink to the surface of Earth, and that's what causes a high pressure area. Because high pressure means you have all of these gas particles that are really close together, making lots and lots of collisions. As they heat up and rise into the atmosphere, then you have a low pressure area because you don't have as many molecules there anymore making collisions. They're now all up here. But what happens is when you increase in elevation, those molecules, especially the water vapor, they're going to cool down because the temperature decreases as you increase in elevation. They will cool down and they will condense back into liquid droplets. The droplets will coalesce into clouds, and eventually, once the clouds become too heavy to support the liquid water, it will fall back down as precipitation. So what's going on here in terms of what's optimal for cloud formation, or what two temperature and pressure values you will see or experience during cloud formation, it's low pressure on the surface of Earth because all of those molecules have gone up into the sky, and then it's low temperature because in order to condense the water vapor, the temperature must be low enough to turn it back into the liquid phase. And that took us to the end of chapter 11. The only other thing that we looked at here was the type of clouds that could form. If you're near a body of water and it's a really, really warm day, you're going to have really large puffy clouds because lots of water are going into the atmosphere, water molecules. If you're inward toward land and it's really cool, you're not going to have the big puffy clouds. You're going to have the sort of wispy thin clouds because there's not a lot of water in the atmosphere. So the size and the type of cloud has everything to do with how much water is in the atmosphere when it condenses to form a cloud.